Hello classes, Mr. Ward. It is Thursday, May 11th. I'm going to apologize for the lack of video for this lesson. The camera must have died, so the video that we recorded in class was lost. I'm gonna do this whole lesson on an iPad, and hopefully you can follow along and get the notes. For section 10.2 about arcs and arc length, we're going to be reviewing archetypes. We're going to be reviewing central angles. We're going to be reviewing some vocabulary terms, postulate 10.1, and the formula about arc length. That's the big focus. Arc length was the focus of today's lesson. Wednesday we really focused on what arcs and the central angles were. So let's jump right in. Let's talk about some archetypes. Obviously these deal with circles themselves. That was kind of the big idea that we were talking about. On this particular circle we're going to call center C, and arcs themselves are going from one edge of the circle to another point on the circle itself. So like point A to point B. This is an arc. It is some fraction of an actual circle, so we're talking about this. This is the arc that's in question. Now, there are different types. This one in particular is called a minor arc. The reason why it is a minor arc, the degree, the central angle right where C is, we'll call that theta. That angle is less than 180 degrees. So it can be anything from an acute angle to a right angle to an obtuse angle. So that was kind of the idea. So anything less than 180. That's the first type that we talked about. Now the second type is called a major arc, and that's pretty much, according to the textbook, it's everything left of a circle. So an actual a major arc would be everything from here all the way to here. That is a major arc. It is all the angle left in the circle. It is obviously an angle that is bigger than 180 degrees, which we actually call a reflex angle. So a major arc is an angle that would be greater than 180 degrees, if that was my thing. Now let's talk about the actual angles themselves. Let's say, for instance, let's say that this angle that's in here, let's say that this one is 20 degrees. That would be my arc measure from A to B. So arc AB, when we actually say arc AB, we're actually talking about the actual distance on an arc. When we put a little m out front, we're talking about the measure of the arc, and that is recorded as the angle on the inside, so 20 degrees, and that's what made it a minor arc. Now, on the other arc itself, the one that we had that was in red, that arc would be everything left of a circle. A circle adds up to be 360 degrees, so this would be 360 degrees minus the 20 that we used earlier. So this would be 340 degrees. And how we'd say that would be the measure of arc A, and we'll call it AEB. And we'll put E somewhere else on the actual circle itself. We'll call this point E. Because when you do major arcs, they have to have 3 letters, not just 2 like a minor arc. Now the final type that we did discuss, that is a semicircle, and let me draw a semicircle here. Make this a little bit larger, and let's go back to black. This is center C again. A semicircle will require a diameter, and diameters go through the middle of the circle, and we'll call this X and Y. And we'll put a point on that circle, we'll call that Z. And that would be a semicircle if this central angle is 180 degrees. So we would, if we said the arc XZY, we're actually talking about the actual distance, the physical distance around a circle, which we'll talk about here in a minute. When we actually put a little M out front, we talk about XZY, with the little arc symbols above it. That is actually the 180 degrees. So remember, the little M out front of your arc symbol, that is the actual central angle measure. All right, that is the different types of arcs. That's how central angles help us define what an arc is. According to Theorem 10.1, central angles and arcs go hand in hand. Two arcs could be exactly congruent to each other if and only if their central angles are congruent. So that's how central angles work. Now, the big thing today, we need to discuss the vocabulary terms, the new terms that apply to this material that we've been discussing. So hopefully you can follow along there. Now, let me clear some of this material out. And let's discuss the vocabulary terms that apply to this circle itself. So we're going to call this circle C again, just like before, and we're going to put a couple different arcs side by side. So I'm going to call this one A and B again, just like before, and I'm going to put another arc right next to it. Let's call this point D. These two arcs, obviously they look like they're minor. It doesn't really matter the type. These two arcs are actually defined to be adjacent to each other. Okay, adjacent arcs, these two arcs in question, they are two arcs that share a point. That is the word adjacent. So let me write that down. An adjacent arc. They are two arcs that share a common point. Now, we have a theorem that applies to this. This first theorem, that obviously, as you can see from our notes, this is postulate 10.1. Did I say theorem? I meant postulate. This is postulate 10.1. The definition of a postulate is an assumed truth in math. It's some mathematical statement we accept. It does not require proof. It's a basis of knowledge that we have to work with. What this particular postulate said was the measure of an arc formed by two adjacent arcs is the sum of the measure of the two arcs. And again, I will type that out for you right here. The measure of an arc formed by two adjacent arcs is the sum of their measures. That is the postulate 10.1. Now let's discuss this let's discuss this postulate. What does it mean for my particular picture? So let me pick a different color here. So on this particular circle, let's say this is 20 degrees, and let's say this is 15 degrees. The arc measure of A to D, that arc would be 35 degrees. That's the measure of arc from A to D. That is from here all the way to here. Now, most people can do that. It's common sense for everybody. But the idea is, the reason why is that it's based on this postulate 10.1. Now, I want to discuss why. What this postulate actually states, and let me put this in a different color. What this postulate says is that you can add the arcs from A to B, like the actual measures of this arc, the measure of A to B, you can add that to the measure of B to D, and that equals the entire measure of going from just A to D itself. And that's how you get the 35, because AB itself was 20, BD, that was the 15, and that's why when you add them together you get 35, and that's the number that I came up with earlier. Now, obviously, common sense, most people don't even need to know the postulate behind it, but that'll be a part of the homework that we're going to be getting, so that's kind of the big deal. Now, let's move on to the actual formula about arc length, and I'm going to use this other circle to help me out here. Now, on this particular circle down here, we're going to be talking about arc length itself. So let's say this is center C, and I'll put, A and B over here somewhere like this. So here's A and here's B. I'm going to keep using those as my points. And, that's a terrible line. Let's go from C to A and C to B. All right, so we're going to be talking about the actual length of this particular arc itself. Now, how to find that length? What we need is we need the angle on the inside, the central angle at the center of the circle. And we also need the radius of our circle. This happens to be the radius, going from the center of the circle to a point on the circle itself. These are the only two numbers that we actually need. Now the formula itself, what it requires to find the actual arc length, so arc length itself, that is equal to, it's taking x divided by 360, and the reason why, when you take x divided by 360, that is a fraction of an entire circle. That is the fraction of the circle for my central angle. You know, we're not going in a full circle, you know, all 360 degrees. We're doing some fraction of it. And we're going to take that times the formula for circumference, 2 pi r. Because if I describe this part right here will give you the fraction of the circle, and this will give you the length of the entire circle all the way around. And when you actually multiply them, that will give you the fraction of the path you're actually traveling on the circle, which is namely this thing that we needed right here. Okay, so let me put in a couple numbers here, and hopefully this will make sense to you. All right, so let me get rid of a couple things here. All right, so let's say that my radius of this particular circle, let's put in some numbers here. Let's say that the radius of my circle happens to be 10 inches. Okay, and this angle right here, let's say this is 30 degrees. So what I'm going to do is I'm going to take 30 degrees divided by 360, and I'm going to take that times 2 times pi times the radius, which is my 10 inches. Now I can rearrange these. I'm going to simplify that fraction out front. What I can do right now is I can get rid of these two zeros. That's a property of simplifying fractions. And now what I'm left with is the 3 over 36, and I can divide both numbers by 3, and that would be 1 over 12. Okay, so that's how I simplify 3 over 36. I divide them both by 3. I'm going to take that times 2 times 10 times pi, and again I rearrange that, and this will be in terms of inches. I rearrange those, that's commutative property, and so I'll get 20 over 12 times pi. So again, this is 20 over 12 times pi, and that's in inches. This number that you're looking at right here, this is the exact answer for a circle. That is the exact distance on the circle itself. Now, if you actually want to find the decimal form of that, you actually have to take 20, divide by 12, and take that number times pi. And what that'll do is it'll actually tell you the decimal form on a calculator. And so that number itself is 5.24 inches. Ooh, that was terrible. That is 5.24 inches. Now again, how I actually did that number, taking the 20, dividing by 12, and then taking it times pi. That number actually gave me this, and this is the actual number that I'm looking for. Now why it turned out to be that? The radius was small, and that angle is very small. You know, I'm not going very far around the circle. My picture here is not drawn to scale. 30 degrees, that would not be 30. 30 is very shallow. The angle that I have maybe here is maybe about 60, 70 degrees if you actually put a protractor right on the actual graph itself. So, but this is the actual formula that you need. This is the one you want to keep in mind. Okay, thank you.